And here we go now to the problems I like to think of as paint defense, or in this case, rate of work done. I say paint defense because this is an older classic math problem where Tom Sawyer is having to paint Aunt Hetty's, or Harriet, I forget which, her fence with the whitewash. And Tom working by himself will take forever. If he gets some help, it would be less time. So what you can figure out from those two times, you can actually figure out if the other person was doing it on their own, which is usually Huck Finn, how long would it take him to do it? Now, this is in math land. When someone helps you, you don't spend time gossiping. You actually both just work. So that's why sometimes we talk about machines instead of people, because the machines, as long as they don't break, do work like this. So I have a odd formula here. So we're going to get how long it takes a particular thing to do one job in a particular amount of time. So that becomes their work rate, their rate of work, their job per the time it takes them to do it. So if I can, instead of the total time it takes, if I can kind of like shift that calculation a bit and instead say, well, how much do they do in one time unit? And you actually end up just with the division of those. So if it's one job in 45 minutes, then we could convert that to hours. And so in an hour, they would do 1 1/3 jobs, 4/3, because of the way the flipping works. So that's what we have here is one job in person A's time ends up calculating to how much they could get done in an hour. Same for person B or thing B, machine B, whatever. How much they could get done in an hour once we crunch the numbers. And then if I add those two, then I get their rate of working together. Because in a set time, one person does their part, the other person does their part. We had the parts they did together, and that's how much they just did. Now I want to point out, though, I have fraction plus fraction equals fraction. The flips of these are not the same. Like it won't add that way. So what I put on top and bottom here is actually very important. All right, let's see what we got here. So you notice the one job, whatever the job is, I don't care. It's just one of those. So the tops of the fractions are all going to start as 1. 1, 1, 1. So one pump can fill a pool in 10 hours. So thing A here can do the job, do the thing in 10 hours. You can write the units here, but eventually maybe not write them for the whole calculation. Working with a second slower pump. So pump B here is going to be slower. The two pumps together can fill the pool in 6 hours. So this 6 is not how quickly the second pump does, but if they work together, it would be 6 hours. How fast can the second pump fill the pool by itself? Or how fast can Huck Finn paint the fence without Tom pestering him? So I very often go with A and B here, like I even wrote person A's time, person B's time. And it might be they give you names of things, you can use those. Variable you pick doesn't matter. So I'm trying to figure out B. And I have ugly fractions everywhere. Yuck, yuck, yuck. I'm going to actually erase the hours because the way I handle fractions, I'm going to write directly onto this. I don't want to see the hours in there. It looks a little confusing. So this I consider math magic. I have all the fractions. I don't want to deal with the fractions. So I'm going to do one step and poof, they go away. The way we cancel fractions, and it must be an equation, is we're going to multiply everything by the common denominator. Now, if you're not sure what the common denominator is, just multiply all three of the denominators. So 10 times b times 6, so 60b. I'm going to multiply everything by 60b. 60b. Now, technically, it's applied to the whole left side, but when we're dealing with fractions, I usually just go ahead and distribute right then. So this one will be times 60b, and then the other side also gets multiplied by 60b. But if you have a term that's being added or subtracted in here that is not a fraction, it will still get multiplied by 60b. We have to multiply both sides of the equation by the same thing. So you have double pan balance. If you double both sides, it stays balanced, or triple both sides, it stays balanced. Got to be the same thing to both sides. Now, the reason we picked 60b is because 10 will divide into there nicely. 10 goes into 66 times, so we have 6 b's. And then over here, the b will cancel with the b, and we just have a 60. And finally over here, the 6 goes into 60 10 times, so we have 10b. Poof! Fraction's gone! I love that. All right, so we have our equation. Now we just got to get like terms together, solve, and figure out b. Now realize here b, sorry, that's my roommate, it's dinner time. B is the rate of time, the amount of time it would take B to do the job on his own. So B is going to be a time number. So let us minus 6B, minus 6B. Now there are 4 B's and 60. Wow, B is very, very slow. Oh, divide by 4, divide by 4. And 60 divided by 4 is 15. 15. Remember, what are the units that I erased? Look back at the original problem. Time. It takes the second pump 15 hours to fill the pool. It's way too long. If you ever had kids, way too long. They are not going to wait 15 hours to play in the pool. But we did answer the question. The second pump does do a considerable amount of work. Together, it only takes 6 hours. That's quasi-reasonable. But there we go. I'm going to stop this one.